Okay, welcome all. We're going to be doing another tutorial, but this time on humeral implant positioning, or positioning of orthopedic implants in 3D bone models. Now, the output of your 3D bone model generation are going to be two .stl files. So those are the ASCII STLs, and those are outputted by Mimics itself as the export file format that you're going to use when taking your 3D bone models and putting them into a SolidWorks part file. Now, it's probably good to mention here that this parsing procedure, once you open up your .stl output files from Mimics, it will take a decent amount of time to parse and process the 3D models into a SolidWorks part file. So you may want to use whatever computer is fastest, if there's a processing computer that's newest, to do this procedure, and then just bring over your files via USB onto a slower computer, as this does use up a lot of your memory. After SolidWorks finishes processing your first bone model, just make sure to save it under your naming convention, and I actually would generally suggest that you exit out of SolidWorks and reopen in order to start parsing and processing your next bone model. So after your bone models have been successfully imported, just make sure you delete any disassociated solid bodies, as it will slow down processing later on. And now we're ready to start creating the assembly. So one key thing to keep in mind when you're creating these assemblies comprised of your exported Mimics parts is you're going to have to make sure your coordinate axes align correctly, as when we bring this file into Abacus, it's going to retain the same origin and coordinate system as it was initially assigned in Mimics. And for material assignment purposes, it's absolutely essential that we align those axes correctly. So just make sure that you normalize the SolidWorks origin with the origin of your cortical or trabecular bone models. So what I'm doing right here is I'm just making sure that the cortical bone model is floating, and then I'm just going to mate it with the origin, ensuring that that align axis check mark is selected. Now, if we've done everything correctly up until this point, when you bring your trabecular bone model in, you'll easily be able to align the axes similarly to in the previous step, where you just mate it with the origin of the assembly itself, and it should auto-align the trabecular bone inside of the cortical shell, so there's no complex positioning that needs to go on after this step. So in order to mimic the surgical procedure by which a humeral stem is usually installed into a patient, essentially what we're doing here is we're mimicking the procedure by which an operating team will position the extramedullary cut guide. Now, in the context of in silico methodologies, we're actually able to perform this procedure much more analytically than a surgical team would. So what I'm doing here is I'm essentially developing a cut plane, or in SolidWorks, a section plane, by which I can calculate, using the SolidWorks Analyze tools, the centroid of the medullary canal at distances 50 millimeters and 100 millimeters distal on the humerus from the peak of the humeral head, in order to determine what the central axis of the humeral canal is. So in order to do this analytically, essentially I'm finding the crest of the humeral head, or I guess the most proximal aspect of the humeral head here, and I'm moving my cut plane distally by, in this case, 50 millimeters, in order to find my first centroid that I'll be using in order to calculate that central axis, or the central long axis of the humerus. Now, in order to perform these analytically, we're going to be using the SolidWorks Evaluate tool, which is under Tools, and we're going to be looking at the section properties, calculating the centroids relative to the assembly origin, and just make sure that you note down these values, as we'll be using them to position points later that will be used to create a central axis along the diaphysis. Now we'll speed up this procedure in a bit, but if you bide with me here, you can see I just extended my section cut down or distally 50 millimeters again in order to develop that second centroid that we're going to use to create the central axis. Now, as we proceed here, we're just going to create 2 points, and using those values that you wrote down previously, you're just going to input these points, and they're going to self-locate at the centroids of the cross-sectional cuts that we made earlier. Now that you've isolated those 2 coordinates, just put a line between them, and you've got your central axis. Now, moving right along here, we're going to have to isolate 3 points at the utmost ridge of the humeral head, so directly adjacent to the anatomical neck. Now, this will provide us with the direction of the retroversion, or the degree of the retroversion of the resection cut. And this is probably the least analytical portion, as we're isolating based on the bony anatomy in this region where we assume the humeral head to be. So now that we've determined our degree of retroversion, we can begin to isolate our lateralization neck shaft angle for our resection cut. Although this process is usually performed using a cut guide, and it's a little bit more arbitrary in the surgical suite, you can see that it's important to at least try to incorporate as much analytical ability as we can in the context of staying consistent, especially between patient models themselves. So as we progress here, we're just going to make use of the mating relations properties of SolidWorks. So right here I'm creating a plane orthogonal to our retroversion angle, and this will isolate the retroversion while discarding the anatomical neck angle, which we're not going to be using going forward. This will allow us to sketch a neck shaft angle relationship between our resection plane and the predetermined central axis that we created earlier. So now that we've determined our orthogonal plane, we're going to start by sketching our neck shaft angle as per the surgical guide, choosing our lateralization while referring to the inferior ridge of the humeral head as our guiding bony landmark. For this particular example, I've chosen a neck shaft angle of 135 degrees to match that of our humeral implant. So now that we've isolated and measured all of our relevant retroversion lateralization and neck shaft angle, of course there's 3 important relationships that we need to take into consideration. The first position relationship is relative to the neck shaft angle, wherein the resection plane must be parallel to the indicated inclination that we defined before. For the purposes of this example, our inclination is at 135 degrees. Our secondary relationship is, of course, the lateralization of our cut, and that we defined earlier as intersecting with the inferior ridge of the humeral head. And of course, the tertiary positioning relationship is the angle of retroversion that we isolated earlier. So our new plane must be orthogonal to the initial plane that we used for calculating our neck shaft angle. As you can see here, after indicating which plane I want to make my cut on, I'm just choosing an arbitrary point and making an oversized circle sketch in order to make that resection cut that one would ordinarily use with or perform in a surgical suite using an oscillating saw. Okay, so now that we've isolated the cut, I'm actually just going to make my trabecular bone model visible, and I'm going to change the color, as moving forward, it'll just make our lives a little bit easier. Planning ahead here, under the understanding that this model will be used for finite element analysis, I'm simplifying my trabecular and cortical bone models as per the literature to 40 mm and 180 mm distal to the center of the humeral head respectively. This both decreases the size of our part files and provides us with a flat surface on which to impose Encastre boundary conditions in abacus. Now, in order to approximate the center of the humeral head, you can see here I'm just using that section properties tool to find the centroid of what is now the new surface of our cut plane in the trabecular bone segment. After isolating the distal coordinates of that center of the humeral head, you can see right here I'm just extending my cut plane 40 millimeters distally in order to create another point which I'll use in conjunction with the central axis of our humeral diaphysis to create another cut plane by which we can shorten the trabecular bone, and then that process is of course repeated for the cortical bone segment as well. Moving forward here, you're just going to have to forgive the pace at which this process proceeds, but if you'd like, you can just skip forward to the next section, which will be the implant positioning part of the tutorial. Now it's interesting, even sped up to 20 times the original pace, this is still quite an extensive procedure in order to get implant positioning correct. But you've finally made it to the portion of the tutorial where we're actually finally doing the implant positioning. Now as you can see here, I'm just starting off by bringing in my SolidWorks implant model, and I'm going to be using this particular model as the master implant for all of my subsequent implant positions. So in this study here, I'm evaluating both this implant as well as a stemless variant and another stemmed variant. But in order to maintain consistency in implant positioning, you don't need to redo the cut planes or really any implant positioning after this step. All you need to do is maintain the same coincentric orientation within the bounds of the trabecular bone and replace this implant with your other evaluation implants that you're going to be using. So most of the implant positioning should be relatively straightforward, but it's probably good just to note that it's absolutely essential that on the implant file itself you develop some kind of relevant coordinate system. So you can see there I've created a couple sketches directly in the implant part file which allow me to choose orientation relative to those original cut planes and positioning planes that we developed earlier, as they're all relevant to the bony anatomy of the 3D bone models that we've developed. Now, as we gradually move forward here, you can see I've chosen our implant orientation relative to the face, but I still need to choose the lateralization of our implant itself. Now, there are a number of different ways to do this analytically, but the main key here is you want consistency with your implant positioning across your patient groups. So you can see here, I've set the trabecular bone model to be transparent, so I can just verify that there's no impingement of my implant on the surrounding cortical bone. Now, as you can see here, I've set a 1 millimeter eccentricity from the center of my humeral stem to the long axis of the humerus, and this convention will be applied to all positionings of my master implant in subsequent patient models. Now, implant positioning is a relatively quick process after you determine your resection plane and all of your initial anatomical landmark directions and axes. But just to summarize the implant positioning metrics, my implant is centrally aligned on the same axis that I used to determine my neck shaft angle, which is of course orthogonal to the resection plane. The implant bone implant surface is naturally mated to the resection surface, and the stem is offset by that 1 millimeter laterally to the central axis of the humeral canal. Now, I guess this is a little bit of an anticlimactic end to our implant positioning, but as you can see here, our implant is now fully positioned in the trabecular and cortical bone, and that trabecular bone has been shortened to 40 millimeters, as well as the cortical bone has been shortened to 180 millimeters distal to the central axis, or I guess the center point of the humeral head. Now, moving forward, this file is just exported as a Step 214 document, and that is now readable by Abacus, so you can bring it into whatever FEA software you're going to be using and begin to do whatever evaluation you're planning on doing with your finite element analysis software. Now, of course, as always, you should do your own literature review to ensure that you don't shorten your trabecular bone or cortical bone too much for your particular study, as your evaluatory goals might be differing from my own here. But hopefully this tutorial has given you a little bit of a baseline on how to get started, at least, with your own implant positioning and resection in the context of, in this case, a humeral RTSA implant. As always, thanks for biding with me while I try and explain this process to the best of my abilities, and don't hesitate to reach out if you have any questions.